part 2 of the video because I accidentally clicked to stop recording. Anyway, so what is an operation in math? We're like rabbit holing. So an operation refers to a process that combines numbers called operands. Oh, so there's an actual word for this. Calling these operands to produce a result. So multiplication, addition, subtraction, or division, essentially it's a mathematical action that you perform on numbers to get a new number. Okay, so are there other operations besides addition, multiplication, subtraction, and division? Like, would something like a derivative or an integral be a different operation? Are there other operations besides multiplication? Oh, okay. Yes. Exponentiation, extraction of roots. Right, so like when we take the square root of something. Logarithm, modular forms, vector addition and subtraction, function composition. Then there's set operations that include binary operations, union, and intersection. Okay. So we indeed have a lot of operations in math, which makes sense. So operations. That's funny. Where does that word come from? Where does that word? Operation originate from? So let's think about the etymology of this. So operation, it comes from the Latin word opus, which means to work, and it can refer to a whole range of practical activities and work, or from the Old French, via Old French from Latin operatio, from the verb operari, which means to expend labor. Okay, so I am understanding how this is all coming together. So we have this word which is called operations, which has its root of work, which means it is an actual action. It is a work. It is a change, right? A sort of change, a process. A mathematical action you perform on numbers to get a new number. Okay, so we're working right now with the basic operations of addition, multiplication, subtraction, and division, or not even that, essentially just addition and multiplication. And I'm quite curious about where this is going to go. And some operations, each one has its like identity, right? So for addition, the identity is 0, because any number that you add 0 to, it remains that number. 200 plus 0 is 200. 1 plus 0 is 1. For multiplication, the identity is 1. 1 times 1 is 1. 1 times 2 is 2. 1 times anything is itself. For subtraction, the identity is also 0, and for division, the identity is also 1. So now that's interesting. We have 0 that can act as an identity and 1 that can act as an identity. 2 might be able to act as an identity in some sort of modular arithmetic or in some sort of like symmetry, rotation type group thing. Maybe? No, maybe not. Don't know. Okay. So, since we're Googling things now, what is that called? Like the place value? The thing that I was trying to say is place value. So, place value is the value of a digit in a number based on its position. The value of a digit depends on its position in a number, even if the digit itself is the same. For example, the 5 in 350 has a value of 5 tens or 50, while a 5 in 5006 has a value of 5 thousands. The order of place value is from right to left is units, tens, hundreds, thousands, and 10,000. So is it called a digit? Like add up all the digits? Is that what I have to add up all the individual digits of x for as many place values as x has? Add the digits. Got it. Digits sounds about right. So as we learn math, we also have to learn the language of math in order to be able to differentiate between these different concepts and define them clearly, because math is in the definition. Math and patterns are in their definitions. So that was a bit of a tangent. So operations and the numbers we're calling operands. Cool. Let's keep going. Okie dokie. So the commutative property itself is based in a certain symmetry, right? So like so much math is based on symmetry and asymmetry. So another way to think of the commutative property of addition is that the idea is that the order of elements does not affect the outcome, meaning you can switch the elements without changing the result, which in itself is a characteristic of symmetry, right? Because that's what symmetry means. A change, like you do something, you complete some action, and you get this, you don't change the result. What is the actual definition of symmetry? Symmetry in math. Okay, in mathematics, symmetry refers to a shape or an object that remains identical to itself when transformed through operations like rotation, reflection, or translation. Oh, so like in shapes and in geometry, the operations that we have are the ones like rotation, reflection, translation, versus with numbers, operations are things like addition, subtraction, multiplication, and division. So for any particular set of, objects or shapes or something, we can define different operations, which is just how we work with those concepts that we have defined, Okay. I am here for this. I am here for this. I didn't realize how much of math boiled down to symmetry in particular. Through operations. So the reason we have all these words is because we have a pattern of things that we can do to a thing, right? Like when we have shapes, all of them can be, moved. All of them can be rotated, and all of them can be flipped. And that's a pattern in which every single this action we're calling translation, every single this action we're calling rotation, and every single this action we're calling reflection. I know this looks messy. That is math. Math is messy. And so that's what all the other operations are with numbers. When we have addition, subtraction, multiplication, and division, it's a pattern of an action that we can perform. And we have given it a name. And all actions that we can, is there like a limit on the number of actions that we can perform? Oh, there's got to be like a basic set, right? After which anything new is going to be a combination of the other ones. So like you can name a rotation plus a reflection its own name, but you don't need to unless like you're using it all the time, because it's just a combination of a rotation and a reflection. So it's kind of like multiplication is a version of addition, right? It's like an exponential-ish version of addition, but we gave it its own name because we use it because we want to work with bigger numbers and we want them to increase faster sometimes. So that's why we gave multiplication its own name, but in reality, multiplication is just repeated addition. So addition is the basic operation, and subtraction is the basic operation. And it's crazy that division sounds so scary sometimes and so much harder than multiplication, right? But division is just repeated subtraction, right? And so, and the way this works is that addition and subtraction are inverses of each other. So if you added something, the way you would get back to it is through subtraction, and multiplication and division are inverses of each other. So if you multiplied by 3, the way that you would get back to your original number was by dividing by 3. But so multiplication is repeated addition. Does that mean that division is repeated subtraction? And I'm thinking about this just kind of with concepts with whole numbers right now, because decimals and things get more confusing, but let's stick to the simple things first. Right, and then exponents, exponentiation is like repeated multiplication. Repeated multiplication. And it has its inverse, which is a logarithm. So, is a logarithm, would that be repeated division? Hold on, let me first answer, is division repeated subtraction? Maybe Google can just tell me that. Is division repeated subtraction? Okay, so yes, division can be considered as repeated subtraction. Essentially, dividing a number by another means repeatedly subtracting the second number from the first until you reach 0, counting how many times you subtracted to get the answer. So to calculate 12 divided by 3, you would repeatedly subtract 3 from 12. So you do 12 minus 3 is 9, 9 minus 3 is 6, 6 minus 3 is 3, 3 minus 3 is 0. So you subtracted 3 4 times. So 12 divided by 3 equals 4. Okay, so since we're following this pattern, right, we have addition and subtraction as the basic operations. We have multiplication, which is repeated addition, division, which is repeated subtraction. Is exponentiation repeated multiplication? Is exponentiation repeated multiplication? Yes, exponentiation is considered repeated multiplication. It is a mathematical operation where a base number is multiplied by itself a specific number of times as indicated by the exponent, right? So like 2 to the power 3 is 2 times 2e times 2. Let me write this down here for a second. 2 to the power of 3 is equal to 2 times 2 times 2, which equals to 4 times 2, which is 8, which is this 2 times 2 times 2 is repeated addition. So you're adding 2 times, which gives you 4, and you're adding 4 2 times, which gives you 8. So, okay. So then logarithm has to be repeated division, right? Let me just double check that the inverse of exponentiation is the logarithm. Yes. Okay. So the logarithm is like, so by the time we get to exponentiation, we're calling this a function now. The natural logarithm function is the inverse of the exponential function. So these are operations, but they're also functions. Okay. So a function is so important in mathematics, science, and engineering that it is given this function is so important, the natural logarithm function. So it's given its own name, which is ln, right? Which is like ln of x or ln x. Cool. Anyway, is logarithm Is logarithm repeated division? Yes. Okay, so logarithms can be treated as repeated division because they are the inverse of powers, and powers are repeated multiplication. But that's the same as my logic. Like, that's the reason Google is saying that logarithm is repeated division is because it's the inverse of this, which is repeated multiplication. So like it's like super easy to see that multiplication is repeated addition, and it's super easy to see that exponentiation is repeated multiplication, but we're in a sense following a pattern here, aren't we, in saying that division is repeated subtraction and logarithm is repeated division, because saying that division is repeated subtraction, that's like, okay, like I can follow along that and imagine that in my mind. Saying that a logarithm is repeated division, now that's really hard for me to like imagine, but I'm like, okay, but it's probably true because we're following this pattern, and logarithm is the inverse of exponentiation and division is the inverse of multiplication, so it has to be that, right? Like that's the proof, no? Kind of? Kind of? Anyway, so here's what I'm noticing, right? I'm noticing that we are like, I feel like almost doing derivatives and integrals on operations, right? Because you know in calculus, you have derivatives and you have integrals. What's the definition of a derivative in math? A derivative of a function, let's see, definition of a derivative. What is a derivative in math? Definition. Google doesn't just straight up give you a definition. That's interesting. It's a tool that quantifies the sensitivity of change of a function's output with respect to the input. Well, okay, so when I'm thinking about calculus, I'm thinking about these following graphs. So let's say we have this graph of f equals x squared. And then we have this graph, right, where f equals 2x. So 2x is the derivative of x squared. So we're essentially moving down a power. Like we're moving down a rate of increase, right? Kinda. Versus like f equals 2, so we're taking away the x, that's just this. And so, geez, I should probably write like g, f, g, h, whatever. I don't know what I'm doing here. So like, how do we write these things? So d of f of x, so the derivative of f of x in this case is going to be g of x, because the derivative of x squared is 2x, and the derivative of g of x is going to be h of x right now. For now, we're just going to do this simply, right? And the integral would be the opposite. So like the integral of h of x is going to, like, I don't know, 0 to infinity or negative infinity to infinity is going to be, this looks funny, is going to be g of x, and then the integral of g of x in this scenario is going to be f of x. Kind of, right? We know the whole plus c constant, whatever, but just bear with me. So the reason I'm connecting these two things right now is because, is there another one? Right? Like, is there another one? Because if we have like another function, So like, let's say this goes 1, 2, 3. We're going up three levels. We're going up a dimension each time. So I feel like don't want to turn the page. Just going to use more paper. So then 4 would be f equals 1/3 x cubed, right? So we're moving up another dimension, essentially. I think. Maybe dimension is the wrong word to use. So what does that look like? Graph of 1/3 x squared supposedly like this, something like that. Right. Okay, the point is, every time that we are taking the integral, it's like we are moving up and we are summing the area, right? So like over here we have negative area and we get to this point. That doesn't... Am I doing this right? Well, okay, so when we get to here, the area continues to increase. It's like the sum of the area. And so then here, the area like increases exponentially instead of constantly. Here, the area increases constantly, so we have a straight line. Here, in the straight line, the area increases exponentially, so we're getting this exponential function. And so then, the next dimension, it would increase even more. Anyway, I already can't visualize the graph of the next dimension. But point is, right, with math, the things that we can't visualize, we can figure out with the numbers if we figure out the patterns. And so, okay, that was like a tangent in itself. But since we have derivatives and integrals in calculus, I feel like this relates to the whole addition subtraction as kind of being like this first constant, first level 1 dimension. Multiplication and division is kind of like the integral of addition and subtraction, because it's the second dimension. It is the repeated version of addition and subtraction. And so then we have the third dimension, which is exponentiation and logarithm. So then my question is there a fourth one? So going by this pattern, we would have something which is going to equal repeated exponentiation, and something else which is going to be repeated logarithm. Is there a verb for logarithm? I'm just going to write logarithm for now. Okay, so let's see. Is there something called repeated exponentiation? Do we have... Oh, we do. Holy cow! I just got myself to something I've never heard of before, and it's called tetration. Whoa, we just followed a pattern into something, didn't we? Ooh, this is fine. Okay, so tetration, which is also called hyper-4, is an operation based on iterated or repeated exponentiation. Wow. Oh, wait. No, of course I've done this. It's like when you have x to the third to the fourth, right? Right? It means raising a number to the power of itself multiple times. Oh, so x to the third to the fourth is going to equal x to the fourth. Wait, x to the third, is it going to equal x to the third times x to the third times x to the third times x to the third? Is that how that works? Because x to the third power is x times x times x. So x to the third to the fourth power, we're just treating that whole variable as its own thing, and we're just multiplying that. Right? Right? I think that makes sense. Okay, so what's the inverse of tetration? Inverse of tetration. Oh. Okay. So there's two inverses of tetration. It's called superroot, and superlogarithm. So I feel like logarithms in themselves confuse me sometimes, and I don't remember how they work off the top of my head. I would have to Google it again. But I feel like that's kind of sad that anything that we continue moving up on, it's going to have to be based on that logarithm. So I got to learn that, don't I? So now, right? So like, it just continues, doesn't it? Could it technically continue infinitely? So addition to multiplication to exponentiation to tetration. So then there would be something which is repeated tetration, no? I don't know if we have its own name for it at that point, but it would be like x to the third, let's just use to the second, right? So that would be x cubed times x cubed squared times x cubed squared, which would equal x cubed times x cubed times x cubed. Oh, that's why you're allowed to multiply these things together. Oh, because 2 times 2 is 4. Oh. Wow. Okay. So, does that mean that x cubed squared, does that mean that I can do 2 times 2 equals 4, and then 4 times 3 is 12? Does that mean that this is the same thing as x to the 12th power? It does, doesn't it? Because then you would just do, right, because this is the same thing as exponentiation, which is just repeated multiplication, which is just repeated addition. So we're just going backwards because it's all connected and it's all related, and that's how it was defined in the first place. Okay. I am following. Oh my gosh, guys, there is a word for it. So repeated tetration is called pentation or hyper 5. Oh, and that's hyper 4. And so then we just keep going, isn't it? Like we just go to hyper 6, hyper 7, hyper 8, whatever, as many times as we want. Ah, that's some sort of infinity there, isn't it? Wow. Wow. Well, and let's think about this, right? Addition and multiplication and exponentiation, those sound like their own words, but I do notice that like when we're starting to get to tetration and pentation, it's like similar words that mean like 4 and 5, like tetrahedron or like pentagon, right? And so What are these words? So this is called a hyperoperation. Oh, and so the next one is going to be hexation, because hex is for 6. So then what are these prefixes from? Is it Latin or Greek? What are the prefix? Terra? Okay, so so this is from Greek. Okay, so now we're using Greek and Latin. So this is from Greek. So what are all of the Greek prefixes for numbers? So let's see. So mono, di, tri, 3, tetra is 4, penta means 5, hexa means 6, hepta means 7, octa means 8, enna, ennea means 9, deca means 10, hendeca means 11, and dodeca means 12, and hecta means 100. So you think people numbered the hyper operations continuing down this way? So since we had tetration as number 4, as the 4th hyper operation, and we had pentation as number 5 and hexation as number 6, does that mean heptation would be hyper 7? Am I right? Am I right? Am I right? What is the 7th hyper operation called? It is heptation or septation. Heptation or septation. Oh, okay. So then would Latin be the other one? The prefixes for the numbers in Latin? Prefixes for numbers in Latin. Is that where the sept comes from? Oh, okay. So we have Greek versus Latin. Okay, so then we have uni, bi. Okay, so that's where we get bicycle from, right? Then we have quad and quint. That makes sense because this is where we get the quadrilateral from. So a lot of words in math have their roots in prefixes of Greek and Latin, right? And so if I pay attention to that, I can find more patterns and I can learn things. It's kind of like September, you know, the word September and the month September, October, November, December, that goes from Latin of sept is supposed to be 7, oct is supposed to be 8, like October is supposed to be the 8th month. That's a whole other conversation, which includes the 13-moon calendar, possibly, that I'm going to a tangent I'm not going to go on, because this is exactly what rabbit holes are like, that I have gone somewhere and I was originally here, and I want to get back to here, but I'm so interested in all of the things that I'm finding. All right, so let's continue. Anyway, I feel like this is very interesting and that it's somehow connected to integrals and derivatives. Like, anyway, the concepts wise. So, I'm going back to this. I want to continue to know more about this pattern of 9. So, let's keep going. 9 times 22 is 198. 9 times 23 is 207. Do you see what I see? Just add this 0 here, and you add this 0 here, and just going down a step. So then I bet you using this pattern, I can tell you that 9 times 34 is gonna be 308. And I can tell you that 9 times and then is it going to be 7? What is this magic? I need to write, I don't know. I need almost cursed. I need a spreadsheet of this, and I need to rewrite this somehow. Okay, pause. Okay. I started something, and I think I've essentially written enough for the patterns. Like I could write out the rest of this without actually doing the multiplication. Because look at this. In the first row, every single first digit is 9. In the second row, every single first digit is 8. In the third row, every single first digit is 7. In the fourth row, every single one is 6. And do we have that, like, over here? Oh, no, we don't, do we? Wait a minute. Wait a minute. Wait. Something here is interesting because in the first row, column. Now we're in columns. In the first column, once we get halfway, which we pass 5, then it starts to mirror each other because we have 45 and then 54, 36 and 63. Then we have this one, which is 144, which doesn't have its mirror, but we do outside of it, which is in this second column we have 153, and then these two numbers become these 35, and then we have 62, and then we have 26. Holy cow. And it's 62 is 63 minus 1. 53 is 54 minus 1. 27 is 26 minus 1. These are like, you know, whoa. Okay, so then third column, do we have that? We have, now we actually start the mirroring a row down. So this one we skip, right? Oh my goodness. Do you see that? So we have 234, and then we have 243, and then here's 25, here's 52, here's 16, here's 61. Then we go another column to the right, and we once again have one number which doesn't mirror. But a 144, right? That's the same thing as a square, right? 144 is 12 squared, from what I remember. So 144 equals 12 squared. What about 133? Is that a square root? No. Okay, so that's whatever I was thinking there, isn't it? 333 divided by 12. What about that? No, that doesn't work either. Okay, so we have a number, some number here. And then, but maybe it has something to do with the 11s, because this has a 44 and this has a 33. So then we're going to skip it. The next one, so we're going to have in column 6, right, which is going to be 37, then we have 47, 57, so in column 5, the numbers are going to start mirroring, like the second two digits are going to start mirroring in row 48, in row 8. So in column 1, the digits start mirroring after row 5. In column 2, we have like a row 6 in which a number doesn't mirror and then the other ones do. Then we have in column 3, the numbers, the last two digits start mirroring after row 6. So then row 7 becomes the number that doesn't mirror. So then in column 5, the digits are going to start mirroring after row 7. So not this one, but this one. And so this one right here is going to be the number around which they mirror, around which the second two digits mirror, and I bet you that number is probably going to be 422. So let's see that 9 times 58 is at 422. 9 times 58. Oh, it's 522. Oh, because I skipped. Okay, I see. So I skipped, because I skipped a column each time, so we're actually adding 2 to that third digit. So that's 500, right? And so we have, let's draw 2 more columns. So then this is going to be 9 times 68, 9 times 78. So in column 7, the digits are going to start mirroring once we pass row 8. So then in row 8, we're going to have that number that does not mirror the last 2 digits, and this one's going to be, so this one is going to be a 711. So 9 times 79 is 711 based on this pattern. Is that true? Yes, I got it. Look at all of the, 9 and all of its patterns. Do you see it? There's a pattern upon which the mirroring happens. Then there's this pattern, do I even have enough colors for all of this? So look at this. All of the first digits in each of these columns go from 9 to 0. And then in all of these rows, we have the first row is 9, the second row is 8, the third row is 7, which is always going to be 10 minus the row number that you are in. And then we can take a look at, let's look at the second digit. So we go from 0 to 9. Then in this second digit, we go from 0. So we go from 9 to 8. Oh my gosh, it's like rotating, right? So then, so we go from 9 to 8. So we go 9, 0, 1, 2, 3, 4, 5, 6, 7, 8. So then in the third column, we start from 8. We go 8, 9, 0, 1, 2, 3, 4, 5, 6, 7. So the next one becomes 7. So watch, I can write out this whole 5th row, right? Without even thinking about it. Because hold on, let me just quickly write out the numbers. So 41, 42, 43, 44, 45, 46, we go 49, 50. So 9 times these numbers, we're going to have in the ones place, so we're going to have the digit of, what are we going to have? So we're just going to have 9 through 0. So we're going to have 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. In this tens place, we're going to have the next iteration of the spinning, which so we started at 7 here, so we're going to go 6, 7, 8, 9, 0, 1, 2, 3, 4, 5. And so then the question becomes, how do we know when we start the 2s versus, this is also its own triangle of where we start the 2s versus the 3s versus the 4s, because here we have the hundreds place. What do we have in the hundreds place? Here we don't have any hundreds place, so we have 0 hundreds place until we get to this point. Then we have 100 in the hundreds place until we get to this point. Then here, so then this one's going to be right here. So we go 2, 2, 2, 2, and then 3s all the way down. Look at that. Look at that. That is so cool. Actually, I did this wrong. This is not supposed to be 2. This is supposed to be 3, and that's supposed to be 4. So, wow, it's getting darker. So this is supposed to be 3, 3, 3, and now we have 4, 4, 4, 4, 4, 4. So, okay. It's supposed to go one more down over here, actually, isn't it? So where's my eraser? No. So, okay, so this one switched after row 1. This one switched after row 2. This one switched after row 3. So this one is supposed to switch after row 4. So this one becomes a 3, and a 4. So in the 5th row, we have 4 3s. In the 5th column, we have 4 3s. In the 4th column, we have 3 2s. In the 3rd column, we have 2 1s. In the 2nd column, we have 1 0 per se in the hundreds place. In the 1 column, we don't have that. But look at the patterns for the 9s are like diagonal and across and down. So it's like we have 10 numbers. So we have 10 digits when we count them, but we actually go from 0 to 9. All of this is mind-blowing, and I feel like there's more in like Wow. So then the question is, this is probably what someone looked at, right? When they essentially figured out like a trick or technique for multiplying any number by 9, they probably figured this out, and they were like, okay, what is the pattern? And then they were like, how can I like mathematically do it so that it's faster than just trying to do long division and long multiplication? I don't really know where this is going, but this feels very like, I've heard of lambda calculus, which is like functions all the way down, in which like, function within a function within a function. I feel like this is a pattern within a pattern within a pattern, and then I don't really know where I'm going with it right now, but yeah. I feel like I noticed my mic stopped working at some point. I was like so into the math. I'm posting this anyway, because it's just me exploring. This is what exploring looks like. This is what learning looks like. This is what going down a rabbit hole looks like, okay? So if you haven't done it in a while, maybe it'll remind you of what it feels like. Maybe you were just doing work in the background alongside with whatever the hell I was doing, and I was just some random person like who just appeared in the library, started talking my own things to myself. Yeah. Anyway, I'm excited. I don't really know what's happening, but I'm excited. And thank you for watching.